So when we say that something has a velocity, the implied question is velocity with respect to what? Right? So when we talk about the velocity of a car, usually our kind of implied reference frame is, well, with respect to the ground, right? The velocity of the car is different than the velocity of the ground. We just kind of internalize that the ground is motionless, so anything that has a speed relative to the ground, like that's its actual speed. But is the ground motionless? Right? Is the ground beneath our feet motionless? No, it's not motionless at all. Anyone know how fast it's moving? Alright. Aha, Ramsey. Good one. Yes. So, Ramsey asks, relative to what? And that is the right question, right? If we say, well, what is the speed of the ground relative to the sun? Well, that's about 32,000 miles per hour. If we talk about the speed of the ground relative to the center of the Earth, well, that's whatever speed is going to cause you to rotate in one full circle in one day. So yeah, with respect to what? Frequently, we will have to do a chain of these questions. So my favorite example is, like, imagine you are on a ferry on a river, or a boat on a river. You want to cross the river. Right? You want to go from one side of the river to the other. But the river itself has other ideas, because it also has a velocity. So if we try to cross the river just straight from one bank to the other, what's actually going to happen? Where are we going to end up on the other bank? So this is kind of a simplified version of the question. We'll deal with the general case in a second. But let's imagine that the river is flowing to the right at 10 meters a second. And that our boat is capable of a speed of about 20 meters per second in still water. Make sure that we realize that the river is flowing in the positive x direction and the boat is trying to cross in the positive y direction. So what's the total velocity of the boat as it tries to go directly across the river? Well, the total velocity of the boat, again, with respect to what? In this case, we're going to say the velocity of the boat with respect to the shore. Okay. That's going to be equal to the velocity of the river with respect to the shore plus the velocity of the boat with respect to the river. The velocity of the river is 10 meters a second in the x direction, nothing in the y direction. The velocity of the boat with respect to the river is nothing in the x direction, 20 in the y direction. And so the net speed, or the net velocity of the boat with respect to the shore is going to be 10 in the x direction, 20 in the y direction. And of course, if we wanted the speed We can use the Pythagorean theorem to get that. Ten squared is 100, 20 squared is 400, so we've got the square root of 500, which is, what, it's about 24 and a half. So the key thing that we want to look at here, so we want to, if we want the velocity of the boat, right, and we want the velocity of the shore, right, we need to make sure that one of the velocities, one of the things that we're considering, has the thing that we want the velocity of, right, and the other thing that we're considering is like an intermediate velocity. So we have boat to river, river to shore. It's like a transitive property sort of thing. So we want boat to shore, and so boat to shore is equal to boat to river, river to shore. Maybe you can actually just add a plus sign there. Do you have any questions on this so far? Okay. No questions? That's good. Let's try a more complicated example. In fact, we're going to do a couple of these. So let's start with this raindrops. So if you're driving during a rainstorm, the raindrops are falling from the sky, maybe completely vertically. We're saying that it's a rainstorm where there's not a lot of wind going on. But you are moving in your car. So what do you measure as the velocity of the raindrops? And maybe like an important related question, like at what angle are the raindrops going to hit your windshield? So maybe we'll add that as a part B. Okay. So we start off the same way as the boat problem. So we want to know, well, what is the velocity of the raindrops with respect to the car? What we have is the velocity of the raindrops with respect to the ground, and we have the velocity of the car with respect to the ground. Let's illustrate this with a picture. Don't make fun of my cars. I'm a physicist, not an artist. That's supposed to be a headlight. So we have a car moving at 22 meters per second. We have raindrops falling at 4.5 meters a second. we can just go ahead and say the car is moving in the x direction and that rain is going to move in the negative y direction. So if we come back here to our vectors, the velocity of the rain with respect to the ground, and also let's check, make sure this actually works like we're thinking of. So rain to ground, car to ground, right? That doesn't actually cancel the way we think, or the way we want it to, right? So if we want rain to car, we're going to need rain to ground plus ground to car. So if the car is moving to the right relative to the ground, what direction is the ground moving relative to the car? Let's see. Mr. Keys, what do you think?
Hello? Hello?
Yep, we can hear you.
Can you hear me? Well, relative to the ground, wouldn't it be going in the opposite direction, so to the left, if I'm not mistaken?
Yeah, that's right. If the car is moving to the right relative to the ground, then the ground is moving to the left relative to the car. Thank you. So we want this to be ground relative to the car. Okay. So the rain relative to the ground is moving nothing in the x direction, negative 4.5 in the y direction because it's falling. The ground relative to the car is moving in the negative direction, and it's not moving in the y direction. So our total velocity of the rain with respect to the car is negative 22, negative 4.5. What angle does this appear to make? Like if you're looking out, in fact, that's a more interesting question. If you are looking out the window as someone else is driving, what angle does the rain appear to make? Anyone have an idea of how to go after that information? See, Kelly John, we know what the velocity relative to the car is. So if we look out the window, what angle is it going to appear to make? Like, at what angle will the rain appear to be falling? You got nothing? That's fine. Prada says rain would be vertical. Well, if you weren't moving, it would appear to be vertical. So from the perspective of the ground, the rain is falling vertically. From the perspective of the car, though, the rain is not falling vertically, it's falling at an angle. Ha! I like Cruz puts some forward slashes in the chat and says this angle. Yeah, that's more or less right. And yeah, we have to find the theta of the VRC vector. So let's go over how we're going to do that. So the velocity of the rain with respect to the car is moving in the negative x direction, and it's moving in the negative y direction. So this is like VRC x, VRCX, this is VRCY, and this hypotenuse here is the total velocity of the rain with respect to the car. So the rain, let's see, what's the most natural angle to measure here for the rain? I think maybe, since we expect it to be vertical, let's measure the angle away from the vertical here. This angle theta. Using the, so we have to use a little geometry. Everyone remember the alternate interior angles theorem? Right, so if this is theta here, then this angle over here, also theta. All right, so we can say the tangent of theta is equal to VRCX divided by VRCY. So 22 over 4.5. And I get 1.37 radians. Okay, so theta is equal to tangent inverse of this thing, 22 over 4.5. It's about 1.36 rads. Morales is 4.8 over 1800. Not sure where the 4.8 and the 1800 come from. Oh, okay. So 1.36 rads, how many degrees is that? About 78 degrees. Yeah, Keys, you're right, 78-ish degrees. Okay. Any questions on this problem before we move on? Yep, I thought that's what was going on with you, Trainmaster. That you were just going after the other angle. That's totally fine. That's why a picture is important. All right, let's pull another question. $70 is a little bit more complicated, but it illustrates an important principle. So let's imagine we have two reference frames. We're calling them S and S prime. So we're being very general about it. We're not actually saying this is a boat in a river. So we have two sets of coordinate axes. So S, coordinate axes of S look like this. But S prime is moving with respect to X, or with respect to S. And in fact, we know we know what velocity S prime is moving with respect to S. So the velocity of S prime with respect to S is 1, 2, 3. Right here we're dealing with a three-dimensional problem. So first question is, can we write down a formula for the position, the relative position of s prime and s, given that we know the velocity. And we do have a little bit of important information here, is that at time t equals 0, they agreed with each other. Their origins were the same, their axes were in the same direction. So at time t equals 0, they were the same reference frame. So the reference frame that we leave stationary we'll frequently refer to as the laboratory frame. Right? So this is the frame that is measuring the movement of some other reference frame, some other object that is moving. And the velocity between these two reference frames will sometimes be referred to as Galilean relativity. So there is a relative velocity between these two reference frames, but that's not to be confused with general or special relativity, which is Einsteinian relativity. So we know that there is a relationship between velocity and position. So position, right, the displacement between s and s prime, has got to be the integral of the velocity. And we'll go from time 0 to time t. Oh, I forgot that there's the t up here. Okay. Is anyone not comfortable doing this integral? Would anyone completely freeze if they had to do this integral on a quiz or a test? All right. I appreciate the honesty, so I will spend a moment going over what we mean by this. So first of all, let's talk about the variables of integration. Right? If it makes us more comfortable, we can make this some other variable, like maybe let's use tau for our limit of integration. That way we don't have the same variable in the integrand and the limits. That will simplify things a little bit. And then we have this this integral on the inside. So if we take this t, factor it into the vector, we're going to try to integrate the vector t, 2t, 3t, dt. And when we have to do an integral in more than one dimension, we just do one integral at a time, like one dimension at a time. So the integral of a vector is just the integral of the x part, the integral of the y part, the integral of the z part. So let's say that explicitly. So the integral of this thing is going to be a vector where we take the integral of t dt, that'll be the x part, the integral of 2t dt will be the y part, and the integral of 3t dt will be the z part. And each of these on their own is a really simple integral, right? So the integral of t dt is 1/2 t squared. And we're going to go ahead and evaluate that at 0 and tau. The y part is the same except for a factor of 2. So the y part will be t squared. And in a moment we'll evaluate that at 0 and tau. And then the z part will be a factor of 3 different from x. So 3/2 t squared, again evaluated at 0 and tau. So when we evaluate, now that once we've found the antiderivative or done the integral, we can plug in the limits. So when we plug in for tau, we just replace t with tau. And for all of these, when we plug in 0 for t, the expression vanishes. It's just 0. So our end expression will be tau squared over 2 in the x direction, tau squared in the y direction, and 3 tau squared over 2 in the z direction. Okay. Do we have any questions on the integration? Does that clear up any panic that people were feeling on an integral like this? All right, cool. Any questions remaining on this part before we move on? All right. So for part A, there's our answer. The relative position of s prime to s as a function of time is tau squared over 2 in the x direction, tau squared in the y direction, and 3/2 tau squared in the z direction. So Eric asks, whenever we see a problem that involves position, do we integrate? You can. So the question, the issue with this question was, how do we get from our given velocity to a position? And actually, we could totally have used our kinematic equations for this one. Because for velocity to depend only on time to the first power means that we've got a constant acceleration. So all of our kinematic equations, k1, k2, k3, would totally have applied here. And if you saw that, you could have just pulled out your kinematic equations. But if you didn't see that, I wanted to show that integration is always an option, right? So if you don't see that you've got a constant acceleration and can use your kinematics, then we can integrate and we can get to the same place. So for going on to part B of this question, in general, will the two coordinate systems, will they agree on the position of an object? Drake, if we measure the position of an object using these two different coordinate frames, are we going to agree on the position of the object? No, nothing. Drake's got. Okay. Calderon. Oh. Keys, you can answer, but you've been really talkative today, so I want to try and make sure that other people are involved as well. But if Calderon doesn't have an answer for us, then it's your turn. This way? Don't know? That's all right. I don't know is always a perfectly fine answer in this class. So Keys, tell us. All right, will the two coordinate systems agree on the position of an object?
Hello. Yes. I don't believe so, especially since S prime isn't S prime the velocity, and then S is kind of just the derivative of that one, so they shouldn't agree. Or am I thinking too much?
Yeah, so the prime here is actually not being used to indicate a derivative. Um,
Um,
right, so
Whoopsies.
physicists are a little sloppy about that sometimes. That just S and
My
S
math
prime
brain
are
got too
two,
hard.
yeah, they're two different things.
Uh, then in that case, I'd still say no because they're two different frames. Even though they agreed on the same thing, they diverge, so they wouldn't agree on the position.
That's exactly right. So in general, if we're going to measure the position of an object in S, right? But we are ourselves in frame S prime, right? So we need to take our measurement and add to it the relative position. And that'll give us the position in S. Part C asks, will these two frames, these two coordinate systems, will they agree on the velocity of a particle? Right? And this one is obviously not, right? So the velocity of a particle as measured in S will be equal to the velocity of the particle measured in S prime plus this thing that we were given. Right? So they definitely won't agree. But will the two frames agree on the acceleration of an object? McHenry, do you have an idea about that?
Before we go forward, I just had a really quick question.
Sure.
Um, why aren't they agreeing? Like when you write Vs equals Vs prime plus Vs prime S, like why are you writing that? What is that supposed to mean? Like
Yeah,
exactly.
so imagine that we had a scientist who was moving along with S prime and another one who was moving along with S. Right? So, for example, maybe this is one of them got on a train, right? So if one of them gets on a train and the other one stays on the ground, and they both see a bird, right? Are they going to agree on what the position of the bird is relative to themselves? Right? And the answer is no. They won't agree. But one of them can figure out what the other one would think for the position of the bird. Does that make sense?
Yeah, I get that they wouldn't think the position of the bird is the same, but how did you get that equation, the Vs prime plus Vs prime S? Like I know they're not the same position, and I know they're not they wouldn't be positioned the same, which I just said that, but how do you know that relationship?
So, don't want to erase that. Let me be a little more explicit with these subscripts then. Let's say that we are measuring a bird. So we want to know what is the position of the bird relative to the coordinate system S. But what we know is the position of the bird relative coordinates S prime, right? The way we got this last piece on the end here is because if we know what the relative velocity of the two coordinate frames is. Say we know how fast the train is moving and in what direction, and we know that our friend back at the station did not get on the train. So if we know the velocity of the train, we know how quickly the gap between us on the train and our friend at the station is increasing. Did that answer your question at all?
Sort of.
So if we see a bird like right outside our window on the train, and we say, oh, this bird is 6 feet, to the right of me. That's this number here. So that bird is 6 feet to the right of you. But what's the position of the bird relative to your friend back on the station? So one way to read this would be the position of the bird relative to the train plus the position of the train relative to the station. Right? So
okay, I think I'm getting it then.
Okay.
I think I get it a little bit more. Yeah.
Yeah, so the location of the bird with respect to your friend, it's the distance from the bird to you and then you to your friend.
Okay, I think I see that.
Okay. So parts B and C tell us that you and your friend won't agree on the position or the velocity of the bird. The last bit is, are you going to agree on the acceleration of the bird? And if we look at the form of Vs prime S here, right? So Vs prime S is equal to 1, 2, 3 t. What is the acceleration between S prime and S? Right? So how do we get from a given velocity to an acceleration? We differentiate. That is exactly correct. So this 1, 2, 3 vector is a constant, so we just have the derivative of t dt, which is 1. So then the acceleration is going to be 1, 2, 3. So the acceleration of the bird relative to our friend at the station will equal the acceleration of the bird relative to us on the train plus the acceleration of us relative to our friend at the station. And this acceleration it's not zero, it's a constant, right? So again, we're not going to agree on the acceleration. So just by getting on a train that's speeding away from the station, we are going to completely disagree with our friend about the movement of this bird in every sense. There is a special name for this sort of reference frame. So S prime is a non-inertial reference frame relative to S. This is going to be important in the next chapter because as it turns out, if you don't agree on accelerations, you don't agree on forces, and that's going to cause all sorts of problems. But on the other hand, any reference frames that are inertial with respect to each other. That means they agree on accelerations. It means they'll also agree on what the forces are causing things to accelerate. And when we analyze a situation, we can choose any inertial reference frame we want and get the same answer at the end. So this is a little sneak peek of what we will care about next week. Any further questions on this problem before we move on?
Yeah, one quick thing. So acceleration is the derivative of velocity, right?
Yep.
Am I wrong, or isn't the isn't the derivative of a constant like 1, 2, or 3 supposed to be like 0?
Yes, but they have a t multiplied onto them.
Oh, right. My bad.
Yep. Good question, though. Excellent question. All right, let's do a nice meaty kinematics problem. Oh, I just had it. Oh, here we go. Let's do this. We have an elephant on the surface of the Earth located at a certain latitude. What is the centripetal acceleration of the elephant resulting from the Earth's movement? So we have a few different pieces here. We actually have somewhat of a picture drawn for us already, but let's complete it. So at this point, which is it just me, or is this radius actually appear to be pointing at Scandinavia? Maybe. But anyway, let's pretend that there's an elephant there. Now again, I am not an artist, so my pachyderm is likely to be lacking. There we go. Okay. Pretend that's an elephant. So the Earth is rotating. For the elephant to stay on the Earth, we know there has to be some centripetal acceleration because this elephant is making a circular path with respect to the center of the Earth. So if you're going to be on a circular path, you have to be experiencing centripetal acceleration. So we've got our picture, our coordinate axis. Let's just go ahead and say that the direction that we are spinning is the positive direction. Notice this is actually going to be a one-dimensional problem. We need, also we're spinning around this axis of the Earth. Also pretend that this picture is drawn correctly and that we don't have to worry about the 23-degree tilt of the Earth, which is in fact a reality. But so then the radius of the circle that our elephant is traveling on is actually not from the center of the Earth to the surface of the Earth, but this thing here. So question one is really going to be, what is that radius? Right? Since we can't finish off our picture without knowing how long this important quantity is. So how do we get at that value? Anyone have an idea? No one's eager to bust out their geometry skills? Alright, well, what I'm going to notice, if we draw a vertical down like this, is that this section of triangle here is the same length as this dotted black line up here. So this length, we call this x. This distance up here is also x. Okay, we have a right triangle here, and so we actually have an easy way to determine what this length of x is. We've been using it to break down vectors for a week now. It's going to be whatever this hypotenuse is, and this hypotenuse is going to be the radius of the Earth, times cosine lambda. All right. So we've got our picture and our coordinates settled. I don't know that we actually have any vectors to break down at this point, although maybe what we just did to find x counts as breaking down vectors. So instead, let's go to pulling out physics. And here we know that an object on a circular path must have an acceleration which is equal to the square of its velocity divided by the radius of the circle it's traveling on. So we did this work to find out what the radius of the circle it was traveling on was. It's going to be re cosine lambda. But what velocity is it traveling at? Anyone want to make a guess?
This rotational speed of the Earth.
Yeah, the rotational speed of the Earth is going to be important. So remember, last time when we were talking about rotational motion, we had this set of relationships. So the angle of a wedge is the arc length over the radius. The angular speed of something is the linear speed divided by the radius. And then the angular acceleration is the linear acceleration divided by the radius. This is all for circular motion. So we know the radius of the circle this elephant is traveling on. If we knew the angular speed of the Earth, we would know, we'd be able to find out what the velocity is. So what is the angular speed of the Earth? Of the Earth's rotation? Anybody? You've lived on the Earth your whole life. You should know how long it takes to rotate. Keys, that's correct. 1 rotation per 24 hours. 1 rotation is 2 pi radians. So yeah, so the angular speed of the Earth is 2 pi radians in 24 hours. Not 2 hours, 24 hours. Really, we'd like to use seconds, though, because seconds that's our SI unit. Most of the time we prefer to use seconds to hours. 1 day is 86,400 seconds. Okay. And this is equal to V over R. Note that this actually gives us a convenient way that we can write our centripetal acceleration. So if omega is V over R, and our centripetal acceleration is V squared over R, we could also equivalently write the centripetal acceleration as omega squared times R. So then our centripetal acceleration is going to be 24 divided by 86,400 quantity squared times the radius of the Earth cosine lambda. Anyone know offhand what the radius of the Earth is? Okay, so we have 12,500 kilometers. That's actually the diameter of the Earth. And then we have two people saying 3958 miles. And please never use that unit in my class again. So yeah, the radius of the Earth is about 6,300,000 meters. 24 squared. I'm going to rewrite this in scientific notation. 8.64 times 10 to the 4 squared. Radius of the Earth is about 6.3 times 10 to the 6 meters. And they suggest that we put in lambda equals 40 and see if we can compare our answer for the tabulated values of the gravitational acceleration. So we're going to go ahead and put in cosine 40 here. All right, first person to calculate this all out gets a fake internet cookie, which is worth nothing except respect. Caught my own typographical error. This is not 24, it's 2 pi. Is that a negative 28,000? Yes. We're definitely looking for a positive number here. All right, let's do this a piece at a time. So the radius of the Earth is right, 6.3 times 10 to the 6 meters. Cosine of 40 is 0.76. Uh, 2 pi quantity squared is 39.5. Nobody else is gonna take a swing. Recorder says 0.037. That does seem a little bit small. Yep, no, you're right. Yeah, using these numbers, we do in fact get 0.026. So clearly we're not going to agree with G here. What is it that we've actually measured? Right? Does this calculation actually give us G, or should we have expected it to be the same as G? Right. I would like you to notice that elephants have weight. That is, their legs have to support their own mass. What we've calculated here is the centripetal acceleration, the minimum centripetal acceleration required to continue on a circular path. That is not the same as the total acceleration due to gravity. It's just the minimum. So the elephant needs an acceleration of at least 0.025 to stay on its circular path, but gravity, the overachiever that it is, provides a lot more than that. Right? 50 times more than that. So this is one of those instances of be careful what you're looking for, or rather be careful you know what it is you're looking for. All right, we are coming up on the end of time for today. I'm going to, you can leave if you'd like. I'm going to go over the quiz question at this point if you would like to stick around and see the solution. All right, so our quiz question today was about throwing darts at a dartboard. Imagine that you can throw darts at 10 meters a second, and then it's asking what's your expected vertical drop by the time the dart gets to the dartboard. Well, we've got a very nice picture started off for us here. We have aimed directly at the bullseye. We aren't going to hit it because the dart is going to drop a bit, and I should use a lighter color. In fact, we want to know how much it's going to drop. And this whole distance from the dart player to the board is 2.4 meters. Okay. So here's our picture. Our coordinate system. It's going to be a little difficult to draw to agree with the picture, but we'll say that toward the dartboard is the positive x direction. That wasn't a very good arrow. That toward the dartboard is the positive x direction, and toward the floor is, we'll just go ahead and make it the positive y direction. So when we go to write down our vectors, we've got our initial position, which we can go ahead and call the origin. Right, we'll just say that this person's hand right here is the position 0, 0. So our final position is going to be somewhere on the wall with the dartboard, and so we'll have gone 2.4 meters in the x direction, and we'll have gone some distance, right? Some vertical drop. Our initial velocity is 10 meters a second in the x direction, nothing in the y direction. And our acceleration is nothing in the x direction, 10 in the y direction. So there I'm rounding g from 9.81 to 10. So we reach in our toolbox now because we're ready. We've done our picture, we've done our coordinate systems, we've written down our vectors, and it looks like we're going to need some kinematics here. In fact, since we've got distance, velocity, and acceleration, let's pull out good old kinematics number 2. So our position, I'm using S's today, our position as a function of time is going to be 1/2 acceleration times squared plus v naught t plus initial position. From the way we've defined our coordinates, our initial position is actually 0. That simplifies that. And then let's take stock real quick of our unknowns. So we don't know how much time it's going to take to get to the board at this point, and we don't know how far the dart is going to drop. So that's 2 unknowns. That is within our grasp. So we can actually write down the x and the y parts of this equation. So if we analyze just the x direction, then at the end of the dart's flight, it will have a position of 2.4. Acceleration in the x direction is 0, so this term drops out. Velocity in the x direction is 10, and then we have t. So right away, that tells us that t is equal to 0.24. So we were lucky. One of our directions was a function of only one variable. We were able to solve for the variable. In the other direction, y, after this time, we're going to be at a height h. That's going to be due to acceleration. So 1/2 10 t squared. Initial velocity in the y direction is 0, so that term zeroes out. Because of our analysis in the x direction, we actually know what t is. So we have 1/2 times 10 times 0.24 squared. We can pull out our calculators. 0.24 squared is about 0.0576 times 10 times 1/2. So 0.288. Yep. So if you're throwing from 2.4 meters away, you can expect your dart to drop about 29 centimeters before it gets to the board. Which means you've got to aim high, like significantly high. Right? 29 centimeters is like the entire diameter of the entire radius of the dartboard. So if you want to hit the bullseye, you actually have to aim up here. And that's the quiz problem. Do we have any questions? All right, thank you all for a good class today. I will see you all on Monday. Eric, the acceleration of gravity points toward the ground. But in this case, I drew the positive y direction toward the ground, so I could write down that acceleration of gravity was positive. If you say that positive is up, then you've got to say that acceleration due to gravity is negative. You're being graded on, like you get, usually you get 3 to 4 points just for setting up the problem, like finishing the picture, drawing the coordinates, breaking down the vectors. You get a couple of points for doing, picking out the, a physics tool, like from your toolbox. You get a couple points for doing the math. You get 1 point at the end for getting the right answer. Yeah, you are welcome, Eric.